Okay, everyone, let's begin with this then. So we are doing difficult questions from 3 papers in this particular session. November 2020, paper 5.1, paper 5.2, and paper 5.3. We want to have a look at these 3 papers today, difficult questions from them. If you haven't yet voted on the WhatsApp group, the poll that's posted there, please do that right now so we can decide which questions we will be doing from each of these papers. So let me have a look at this quickly first, the questions that you've asked from this one. Okay, so from this paper, most of you have actually asked about questions 6 and 7 in particular, right? Questions 6 and 7. Now, let's have a look at them quickly. I'll go through the rest of them quick as well, and then see if there's any others that also look kind of complicated. We could have a look at them as well. All right. Okay, so first question looks fairly straightforward. You need to make sure that you understand this notation. Intersection means when both of those conditions are true at the same time. For cases like these, when you have 2 fair die thrown, it's often helpful to make a 2-dimensional table or something. In this case, you could make a sum table if you want for event B. For event A, it's not that complicated actually. You can just do it directly. For B, you could make a sum table if you want to. But it could have been done without that as well. Question number 2 is a probability question. Okay. Question number 3, geometric distribution, and then binomial probability distribution table. Okay, so from this paper, you're asking about questions 6 and 7 in particular. So we'll just have a look at them quickly then, because the rest of the questions, they do not really look that complicated. Okay, so let's start with this one. Question number 6. What about this? So the first part is just about cumulative frequency curve. I hope you can all do that. And then it says 24% of the students take k minutes or longer to complete the challenge. Use a graph to estimate the value of k. Calculate estimates of the mean standard deviation of the time taken to complete the challenge. Okay, which particular parts of this? Those of you have asked about question number 6. Which particular parts do you want to do from this paper? From this question number 6. Is it the whole question? Okay, so let's start with this. Cumulative frequency curve. It says times t minutes taken by 150 students to complete a particular challenge. They're summarized in the following cumulative frequency table. You've got this table. It says draw a graph to illustrate this data. Now, for a cumulative frequency graph on the vertical axis, you need cumulative frequency, right? That's what you have on the vertical axis. I'm sorry, let me get back to that page. Yeah, on the vertical axis, you need cumulative frequency. So we could draw a vertical line here like this that represents the y-axis. On the horizontal axis, you have whatever the variable is. We'll see what that variable is in a moment. Let's draw this for now. Okay. So we've got the horizontal axis here, the vertical axis here. On the horizontal axis, you have time. You have to label that. Time is in minutes. So you'll say this is time in minutes. On the vertical axis, you have cumulative frequency. So you should label that here as well. You can either write fully cumulative frequency or you can just write CF. That's also acceptable. Now, what's the scale that you should be taking? Now, on horizontal axis, you want to go up to 100. So you could do something like this. If you start at 0 here, you could take an interval of 10. Yeah, so that works. 20, 40, 60, 80, and 100 on the horizontal axis. On the vertical axis, you want to go up to 150. 1, 2, 3, 4, 5. Yeah, so we can go all the way up to 150. Let me mark like this. 20, 40, 60, 80, 100, 120, 140, and then we have 150 somewhere as well. Okay, let's mark those points quickly. These are the points that you have to mark: 20, 12, 30, 48, and so on. So what's the first point? 20 and 12. At 20, we've got 12 on the vertical axis. This is the first point. And then at 30, we have 48, 30 and 48. That will be here. At 40, we've got 106. That will be here. And then at 60, we have 134. 60, 134. And that will be this point here. And then finally, at 100, we have 150. 100 and 150, this is the last point that we've got. You can draw a cumulative frequency curve through these points now. The curve is going to look like this. Make sure that you do this with a pencil. It should be a smooth curve like this. If you look at earlier papers, maybe this one as well, they used to allow drawing straight lines. That's not allowed anymore. So please don't do that. Don't make straight lines through these points. Even if you find that to be acceptable in some old marking scheme, they do not allow that anymore. Okay, so you have to draw a curve here. Straight lines are not allowed. You should draw it with a pencil so that if you want to erase and improve something, you can do that. Now, the curve always has to reach the horizontal axis. You always have to join it with the horizontal axis at the end. Otherwise, you would lose a mark. Okay, so it has to reach the horizontal axis. This is what the curve looks like. Okay, that's the cumulative frequency curve in the first part. Now it says 24% of the students take K minutes or longer. Okay, 24% of students. Let's focus on that first of all. How many students do we have in total? We have 150 students in total. What is 24% of that? What's 24% of 150? 150 into 0.24, that's giving me 36. 36 students take K minutes or longer to complete the challenge. Use a graph to estimate the value for K. Now, how do we think about this? Whenever it says some value or more than that, remember we have to look at the right side on the horizontal axis and in the upwards direction on the vertical axis. Let me explain what that means. So 24% students take K minutes or longer. Now, let's assume K was somewhere here. Now, I'm just explaining the concept first of all. Let's assume K was somewhere here. Let's say it was 70, right? Let's assume. Now, what that means is 70 minutes or longer. That means 70 to 100. These are the people that we're talking about who take between 70 and 100 minutes. On the graph, what's that region? That's this region. That's this region on the graph. So vertically, you would also just look at this region from 140 to 150. These would be the 10 students that you're talking about, right? So since they're saying K minutes or longer, this K is going to be somewhere here, and you will be looking at the right side of that. If you're looking at the right side here, on the vertical axis as well, we would be looking at the upwards direction. Now, let's go back here. It says 24% of the students, they take K minutes or longer. 24% of 150 is 36. We will be counting 36 from top, right? For the reason I just explained. From the top, 150 minus 36, what does that give you? That gives you 114, right? This is the value that you will be reading on the vertical axis, 114. Now let's go to the graph. This is 150. 150 minus 36. That's giving you 114. These are the 36 students that we're talking about. This point here is 114. You will be reading this point on the graph. Go on the right side here. What do you get from this? This is slightly smaller than 44. This is the value that I'm getting on the horizontal axis. Now you could write it as either 43 or 44. Both should be acceptable. Improve this slightly here. Now this number here, you could say it's either 43 or it's 44, and that will be your final answer. Okay, so you can round it off approximately. You can see what that number turns out to be. Now, since the point is close here, since the point is in this region, what you should also do is make sure that your curve in this region is drawn as smooth as you can possibly draw it, okay? So that your answer turns out to be accurate. Now this, I can say this is 44 for me, or 43, I could write any of those numbers. And that's the value of k that you would write here, that there are 24% of the students who take more than 44 minutes to complete the challenge. Okay, that's the result that we have here, k equals 44. If it said less than k minutes, then we would be counting those 36 students from the bottom. And we would be reading this value here, corresponding to 36. But since it's saying more than 36 minutes, we count from the top, right? Because this part of the curve is relevant, right? K minutes or more on the horizontal axis, that means this side. On the vertical axis, that means this side. Make sense? So the value of k that we get in this case is 44. Is that okay? Make sense? No problems? Let's move on. Part C. Now it says calculate estimates of the mean and the standard deviation of the time taken to complete the challenge. Now we need to find mean and standard deviation for this data. Now the data that we're given is a cumulative frequency table. This is not a normal table. For finding mean and standard deviation, for group data, we use the formulas sigma fx over sigma f, etc. Now I'll write those formulas here. This was the table that we're given. Right, this is the table that we're given. Now the formulas that we've got for mean and standard deviation, they look like this. X bar is given by sigma x f over sigma f, and standard deviation of x, that is given by sigma x square f divided by sigma f minus mean squared and then square root of that whole thing. That's the formula. These are the formulas for mean and standard deviation. Now, f represents frequency, it does not represent cumulative frequency. So we are not going to be using cumulative frequencies. We want frequency instead. And x represents the midpoints of the intervals. Now, the problem is we don't have intervals here. We just have one-sided inequalities like this. So we want a normal frequency table for this data. How would we do that? The intervals are going to look like this. It's time. Time has to start from 0, right? And the first interval is until 20. We can say the first interval, therefore, should be from 0 to 20. And then the next one would be from 20 to 30, and then 30 to 40, and then 40 to 60, and then 60 to 100. We find the corresponding frequencies. We've got cumulative frequencies here. Let's find the corresponding frequencies. Add another row to the data that represents f. Now, from 0 to 20, we've got these 12 people. Then it says the total number of people less than or equal to 30. What's that? That is 48. So what's the number of people between 20 and 30? Well, the total number is 48, less than equal to 30, less than equal to 20 is 12. What we can do is we can subtract from 48 this 12 to get the number for this part. 48 minus 12, that is 36. So between 20 and 30, we have 36 people. And you now just keep repeating this process. The next number is going to be 106 minus 48. What's that? 52 plus 6, that's 58. 134 minus 106, that will be 28. 150 minus 34, that will be 16. And then you can confirm that these values are correct by just adding all of them up. If they add up to 150, most likely your calculation is correct. So you've got frequencies now. Now you've got the f that you needed here for these formulas, right? The frequencies. Now, what about x? X is supposed to be the midpoint. So now we find midpoints of these intervals. We add another row to the data, 0 to 20. What's the midpoint? Midpoint is 10. And then 25, 35, 50, and 80. These are the values of x that we want to use. And these are the values of frequencies that we want to use. And then it's like a standard frequency table. You can find the mean from this data, standard deviation from this data. I'm sure all of you can do it after this, right? So you just add another row to the data, that's xf. Add another row to the data, that's x square f. Evaluate these. Put this in this form, put the values in this formula and in this formula. You can do it after this, right? All of you can do this? Yes? Any problem after this point? Okay, good. So you should be able to apply these formulas after this, right? This is standard method for calculating mean and standard deviation after this point. Once you have the frequency table, this is what it looks like. You'll just use this to find xf, x square f, then you'll find sigma f from this, sigma xf from this, and sigma x square f from this. Input those values here, you'll get those two numbers for mean and standard deviation. Let's move on. Okay, so this is the next number this is the next question that you're asking about. Find the number of different ways in which the 10 letters of the word shopkeeper can be arranged so that all three E's are together. Okay, so what we want is that all three E's are together. How many letters do we have in total? 10 letters in total. We can use this box's representation. We can say, okay, we have 10 letters in total. 10 letters means we would have 10 spaces or 10 boxes. This is what it would look like. We have 10 boxes for those 10 letters, but then the E's have to be together. What we do is we put the E's in one single box. We merge 3 boxes and put the E's in that big box. Okay, now what are the remaining letters? The remaining letters are S, H, O, P, K, P, R. These are the remaining letters. Okay. Now, how many boxes do we have now? There are 8 boxes. In how many ways can we arrange them? 8 factorial ways. Are there any boxes that are identical? Let's look at the rest of the letters. Are there any repetitions here? S, H, O, P, K, R. Okay, so P is repeated. P is coming twice. We've got P here and P here. So we have to divide by 2 factorial because of that. There are 2 P's, right? In these 8 boxes that we've got, there are 2 P's. So we have to divide by 2 factorial because of that. Okay. And then in how many ways can you arrange these 3 E's? Well, the E's are all identical, so we don't have to arrange them. Right? Even if you were to try arranging them, you would say, okay, there are 3 letters, 3 factorial, but then all of them are identical. We divide by 3 factorial. That becomes 1. You can just ignore that as well because E's are identical. You don't have to arrange them. This is the result that you get. 8 factorial over 2 factorial. What do we get? 20160. That's the result that we get from this. Okay, 20160. Let's move on. Now it says find the number of different ways in which the 10 letters of the word shopkeeper can be arranged so that the P's are not next to each other. So now we want that the P's are not next to each other. How many P's do we have in total? We have 2 P's. We want the P's to be separated. Now, since there are only 2 objects that we want to separate, we can use both the methods that we know about, total minus together or the dashes and stars method. Both methods would work in this case, right? Because for separating two objects, it doesn't make any difference. You can use any of those two methods. So what do? Let's do total minus together. Total arrangements without any restrictions minus the arrangements with two p's together. Now, what are the total arrangements where we don't have any conditions? 10 factorial, because all letters, the number of letters is 10. But then we have 3 e's, we divide by 3 factorial because of that. We also have 2 p's, we divide by 2 factorial because of that as well. These are the total arrangements. Okay. Now, if we want the 2 p's to be together, what do we do for that? We put those 2 p's in one single box, right? We have to subtract this case, right? We put those 2's in one single box. If we do that, let's see what we get from that. Again, you can do this mentally as well if you want. Or if you think this would help you, this representation, you can use this. There are 10 boxes in total initially. There are 10 boxes like this. What you want is, you want the p's together. So you merge 2 boxes and put the 2 p's in that box. How many boxes do we have now? 10 boxes. So we had 10 earlier. Now it's 8 remaining boxes plus this merged box. That's 9 boxes. Now we've got 9 boxes. So there are 9 factorial ways of arranging them. However, in these 9 boxes, there are 3 e's as well. Okay. So we divide by 3 factorial because of those 3 e's. And then we think about the 2 p's. Can we arrange p's in any way? They're both identical. We don't have to arrange them. If you wanted to do that, that will just be 2 factorial over 2 factorial. We can just ignore that as well. And that should give us a result. Subtract from the total the arrangements with the p's are together. So that's 9 factorial over 3 factorial. And that should give you the final result. You can see what that turns out to be. Okay. What's this number? So this is 302,400 minus 60480. And that's giving me 241920. That's the result that we get. Okay, that's what you wanted. Fairly straightforward, part B. Now it says, find the probability that a randomly chosen arrangement of the 10 letters of the word shopkeeper has an E at the beginning and an E at the end. So now we need to find probability. Probability means number of favorable outcomes divided by the total number of outcomes. In arrangements, we can always do number of favorable arrangements divided by the total number of possible arrangements. Now we already know the total number of possible arrangements. That's basically this: 10 factorial over 3 factorial and 2 factorial. We found that in the previous part. Now, let's consider this scenario. We need an E at the beginning and E at the end. Now, the E's are fixed. These 2 E's are fixed. What are the remaining letters? We have 8 remaining letters after this. They are going to come in the middle, right? Apart from these 2 E's, we have 8 other letters. So we have 8 boxes for those 8 letters. There's no condition on those 8 letters. Now, what are those letters? S, H, O, P, K, P, E, R. These are the remaining letters. In how many ways can we arrange these remaining letters? 8 factorial, right? Because there are 8 letters. Remember, E's are fixed. They are not going to move. So they are just fixed there. We don't have to do anything with them. What's the number of ways of arranging these 8 letters? 8 factorial divided by 2 factorial for the two P's, because the P's are identical. The rest of the letters are all different. Okay. And that gives you the number of possible arrangements when the 2 E's are at the ends. 8 factorial divided by 2 factorial, that is giving me 20160. What's the probability of this case? The probability of this case would just be 20160 divided by the total number of arrangements. They were 302,400. And that should give you this probability. Okay, you can see what this turns out to be: 20160 divided by 302,400. And that is giving me 1/15. And that should be the result that we get from this, 1 over 15. Okay, that's your final answer. Fairly straightforward. Now it says 4 letters are selected from the 10 letters of the word shopkeeper. So now we are selecting 4 letters out of these 10 letters. Find the number of different selections if the 4 letters include exactly 1 P. So the P should be only 1. We should only have 1 P. Now, what we do for cases like for questions like these is we make different cases for the repeated letter, right? Because combination does not work directly on this. We can't, for example, for finding the total number of combinations here, 10C4 would not work because we have repetitions here. Combination notation does not work well with repetitions, okay? What you have to do is you have to make cases for the repeated letters. Which letters are repeated? P's and E's, okay? Now, for P, we have this condition. We need exactly 1 P. Okay, so what are the cases going to be? With 1 P, remember we have to select 4 letters. So 1, 2, 3, 4. We have 4 places. We need exactly 1 P. So 1 P has to be there every single time. What about E's? For E's, we could say the possibilities are we could have no E. That's one possibility. We could have 1 E. We could have 2 E's. Or we could have 3 E's. Right? These are all the possible cases. Now, what are the remaining letters? We have made cases for the repeated letters, P and E. The remaining letters are, let me write them on the side, S, H, O, K, R. Right? That's 5 letters and P's and E's. Yeah. So these are the remaining letters, S, H, O, K, R. Now, in the first case, for instance, we want 1 P. In the first case, we want 1 P, right? Now, if we want 1 P and no E, we have 3 remaining places. From these 5 letters, we have to select 3 more letters. So that is 5C3. Okay? Then in the second case, we have 1 P and 1 E selected already. We have 2 remaining places. That means from the remaining 5 letters, we have to select 2. In the third case, we have 1 P and 2 E's already there. For the 1 remaining place, we have to select 1 from the remaining 5. And then finally, in the last case, we have P, E, E, and E selected already. That means from the remaining 5 letters, we have to select none. What's 5C3? 5C3 is going to give you 10. 5C2 is also going to give you 10. 5C1 is 5. 5C0 is 1. Add all of those cases, and the total number of different selections turn out to be 26 here. And that is what we were looking for here. Okay, that's the number of selections that we get. Is that okay? And that's the last question from this paper. Now we would want to move on to the next paper, which is paper 5.2. Why does it not work with combinations? Well, both permutation and combination notation, both NPR and NCR, they do not work when you have repeated letters, okay? They can only be used for different objects, okay? For the repeated objects have to be handled separately. In arrangements, we could handle repeated letters. In permutations, we could handle repeated letters like this, for example, like we did here. In arrangements, we could just divide by the factorial of that, right? To handle those repetitions. In combination, we don't have any such method, right? We don't have any method to calculate, to basically eliminate those repetitions directly. In combinations, such a method does not exist. So for that reason, we have to list down the possible cases. We can't do it directly. What if we divide by the combination by the factorial of repeated letters? Well, that does not make sense. Factorial of the repeated letters, this is basically about arrangement. You divide by 2 factorial because you want to eliminate the arrangements of P here. For example, 8 factorial is considering these P's to be separate, these P's to be different, okay? But the P's are actually identical. 8 factorial is considering that P1 into P2, P1 and P2 is one arrangement and P2, P1 is another arrangement. But practically, they are actually supposed to be the same. To eliminate these cases, we divide by 2 factorial. Factorial is the number of ways to arrange this. When we're talking about combinations, we are not arranging objects. So factorial is not going to be relevant here, right? Because factorial is used for arrangements. So that's not going to work here. We can't divide by 2 factorial. Okay. Why are we separating e's as well? Why are we separating e's as well? Well, because e's are also repeated. It's not that we would just make cases for the letter for which we have conditions. Whichever object or letter is repeated, we have to make cases for that. Okay? Because the problem is, let me give you this example. Let's say you have AAB. And what you want to do is you want to select 2 letters from this. If you do 3C2 directly, what does that give you? That gives you 3 possibilities. But actually, there are only 2 possible 2-letter selections that come from this. And that they are AA and AB. These are the only 2 possible selections that you can get. But if you do 3C2 for selecting 2 letters out of these 3, that gives you 3, and that's wrong. The reason for that is 3C2 assumes that all of these letters are different. So 3C2 is assuming that this is A1 and this is A2. So 3C2 is giving you 3 possible combinations, and they are A1B, A2B, and A1A2. But we know that these 2 are actually supposed to be the same. Okay? Since these are supposed to be the same, they have to be counted as 1. So combination notation does not work here, because combination notation assumes that everything that you're inputting into this, so these 3 objects that you have, out of which you have to select 2, combination notation assumes that they're all different. If they're not different, we can not use it. Okay? And whichever letter is repeated, then what you have to do is you have to make cases for that. Okay, this is a standard method that works for every single problem like this. Unless, of course, you're finding probability, for which we've talked about how you have to treat all letters as different to find that probability. We've talked about that in the last couple of classes as well. But you have to make cases like this. Okay, there's no other possibility. All right, so that was paper 5.1. November 2020, paper 5.1. Let's move on to the next one now. So now we want to do difficult questions from P52 from the session November 2020, P52. Again, please let me know the questions that you want me to discuss from this paper. P52. The question that you find difficult from this paper. Let me have a look at the poll as well. Okay, so this is the next paper we want to look at. November 2020, P5 variant 2. Please respond to the poll if you haven't already, so we can discuss the questions that you find difficult from this paper. All right, so from this paper, I see most of you are asking about questions 2, 5, and 6. Okay, questions 2, 5, and 6. Let's have a look at those 3 questions from this paper. Questions 2, 5, and 6, right? There's no other question that you asked about. Okay, so let's start with this. November 2020, paper 5, variant 2. So the first question is about binomial, and again, binomial. You have this discrete random, or it's just probability, or discrete random variables, distribution table, expected value weights. Okay, so the first question that you're asking about is question number. Okay, so you asked question number 2 as well. Sorry. Okay, so let's have a look at this. Question number 2 from this paper. That's the first one that you want me to discuss. Okay, so it says a bag contains 5 red balls and 3 blue balls. 5 red balls, 3 blue balls. Again, just a reminder, In S1, please make sure that you take your time to read the question statement. Do not rush into just starting with the solution. Read the question statement very carefully and a bit slowly, and that will help you not do many careless errors. Okay. So you have a bag that contains 5 red balls and 3 blue balls. This person takes 3 balls at random from the bag without replacement. The random variable X represents the number of red balls that she takes. Show that the probability. Other account. Can you guys still hear me? Okay, I'm back now. Can you guys still hear me? Oh, good, thank you. Okay, so this person takes 3 balls at random from the bag without replacement. The random variable X represents the number of red balls that she takes. Show that the probability that she takes exactly 1 red ball is 15 out of 56. Okay. Now she's taking out 3 balls, right, at random. Now, what are the possible cases for her taking exactly 1 red ball? One possibility could be that she takes a red ball, and then the first time, and then the second time she takes out a blue ball, and then the third time she takes out a blue ball. And then another possibility could be that the first time she takes out a blue ball, and then a red, and then a blue. Another possibility could be that she takes blue balls the first 2 times, and then a red ball the third time. These are the 3 possible cases you would have. You can make a tree diagram for this as well, and these will be the cases that you get from that. Right? It's not going to be a very big tree diagram. We'll have 2 branches every single time. So 8 branches for the last step. That's not going to take that long. You can do that. We might actually need to do that for the next part. Yeah, probably. Okay, so RBB plus BRB and BBR. What are the probabilities now? RBB. So if you have a red ball the first time, what's the probability for that? 5/8 into blue ball the second time, that's 4/7. Sorry, 3/7. And then 2/6. That is what we get the first time. Now, if you think about it, the numerator is always going to be 5 into 3 into 2 in each of these cases. You can write one more to confirm this. What is going to be the second case? The second case is going to be 3/8 for the first blue ball, and then 5/7 for the second for the second red ball, and then 2/6 for the third blue ball. Now think about it. In the numerator, you've got 5 into 3 into 2, 3 into 5 into 2, 8 into 7 into 6, 8 into 7 into 6. These are basically the same probabilities that you have to add. Now, a quicker way of doing this could be, for now, let me just write this as well. This is going to be 3/8 into 2/7 into 5/6. And that will give you the result. A quicker way of doing such problems is you say, okay, out of the 8 balls, let's actually consider just one scenario, RBB. What's the probability for this? 5/8 for the first time, and then 3/7, and then 2/6. And then you think about in how many ways can you arrange this? So on a tree diagram, you would have red, blue, blue. That is one possibility. That gives you 1 red and 2 blue. And another possibility would be that you have blue, and then red, and then blue. Another possibility would be that you have blue, and then blue, and then red. Right? There are 3 cases that will be there on the tree diagram. Of course, this is not the complete tree diagram, but these will be the 3 parts that are giving you the same probability. So the way to do such problems is you just find the probability for one such case, and then you think about in how many paths on the tree diagram that you can find for this. We listed those paths up there. A direct way of doing this could be You could say, okay, how many ways can you arrange this? There are 3 letters, that's 3 factorial. But then 2 of them are identical, 3 factorial over 2 factorial. This is basically 3. And that is giving you these 3 cases. So what you can do is find the probability for just one of these cases, multiply that by 3, and that will give you that final result. Okay, you can see what this turns out to be. 5 into 3 into 2 divided by 8 and 7 and 6 multiplied by 3, and that's giving me 15 over 56. This is one possible method. This is what you can use here. Okay. Now, another way to do the same thing is using combinations. This is one possible method. In fact, this was one possible method in which we listed down all possibilities. And then another possibility is that we just find one case, multiply that by 3. Or you could also use combinations like this in cases where you have something being taken out without replacement. In cases where you have without replacement, condition mentioned, you can also use combinations. And that works like this. You can say, okay, we want exactly one red ball out of how many balls? Out of one red ball out of 8 balls. Yeah, out of 5 balls, sorry. These are 5 balls, so you're not distracted. Okay, so you have 5 red balls, you want 1 red ball, and out of 3 blue balls, you want 2 blue balls. So you can also think of it like this, that since you want exactly 1 red ball, you say out of 5 red balls, select 1 red ball, 5C1. And out of 3 blue balls, select 2 blue balls. These are your favorable outcomes, the outcomes that satisfy the given condition. Okay, that out of 5 red balls, you want to select only 1, and out of 3 blue balls, you want to select 2. Okay. Can you guys still see my screen? Can you see me writing? Okay, maybe there's a lag because on my other device, I can't see that. Okay, all right. So 5C1 into 3C2 divided by the total number of possible combinations. What's the total number of possible combinations? Out of 8, we have to select 3 balls, so that's 8C3. And that could also give it the same result. You can try this. 5C1 multiplied by 3C2 divided by 8C3, and that gives you the same result as before. That is 15 over 56. This could be another possibility. Now, the thing is, you have to know both of these methods, both methods. The reason for that is sometimes figuring out all of these cases on the tree diagram, it becomes quite complicated. And the combination method makes it much easier. But the combination method cannot always be used. Combination method only works when you have without replacement here. If you had with replacement, that means the probabilities were not changing every time. Then you would have to think of these cases. So this method would work every time, but sometimes it gets a bit too complicated. And that is where the combination method is going to help you simplify things. Okay, but remember, the combination method will only work when this is without replacement. Otherwise, it would not work. Is that okay? Any problem with this? Because if you understand this first part, then the second part is just doing that same thing over and over again for the other possible values of x. Any problem with the first part? Because if you understand this, the second part is fairly straightforward then. Okay. Now, in the second part, it says, draw up the probability distribution table for x. That means you want some values of x and corresponding probabilities of those values of x. Now, what does x represent? X represents the number of red balls taken. What could be the number of red balls? You're taking a ball 3 times. X could either be 0, right? You might have no red ball. You could have x equal to 1, or x equal to 2, or x equal to 3. These are 4 possible cases that you have. Now, when x equals 1, What's the probability for that? We already know that. We have found that 15/56. This probability we've already figured out. What about the other cases now? Now you can use any of these methods that you prefer. I would say combination is much quicker in this case, but it's your choice. You can also do this. This also works. X equals 0. What does that mean? The denominator is going to be the same. Out of 8 balls, you want to select 3 balls. In the numerator, if you want no red balls, what does that mean? Out of 5 red balls, you select 0. 5C0. Out of 3 blue balls, you select all 3. And that will give you this first probability. That's 1 into 1 divided by 8C3. What was 8C3? 8C3 was 56 here. This is 1/56. And then probability of X equals 2. What would that be? Out of 5 red balls, select 2. Out of 3 blue balls, select 1. Divided by 8C3. And that will give you something. 10 into 3, I think that's 30/56. And then you can do the same thing for X equals 3 as well. I would recommend if calculating the probability is fairly straightforward, like in this case, calculate each of these probabilities rather than doing one minus that, because you can just then verify your answer as well. So let me explain what that means. Find the probability of X equals 3 as well. Let's see what that turns out to be. That would be 5C3 into 3C0 divided by 8C3. Now 5C3 is 10. 10 into 1 divided by that, that's 10/56. Now the probabilities turn out to be 1/56 here, and then 30/56 here, and then finally 10/56. And now you can verify your answer. Add all of these probabilities, they should add up to 1. So 16 plus 40, that's 56/56. They do add up to 1, so that's most likely going to be correct, because the probabilities are all adding up to 1, and that's your probability distribution table. Okay? That's the second part of this. Then the third part, you're given that expected value of X is 15/8. Find the variance of X using that. Now, that's a standard process. You can do that, I suppose. You've got the expected value given. So all you have to do is just add another row to the data that represents X squared times P. XP is not needed because they already have given you the expected value. What's X squared P going to be? 1/56. Sorry, 0. 15/56. 2 squared is 4. 4 into 30/56. That is 15/7. And then 9 into 10/56. And that's 45/28. You can add all of them up. You'll get sigma X squared P from this. What's that? 15/56 plus 15/7 plus 45/28. And that's giving me 225/56. Just put that here in the formula. Variance of X. What's the formula for variance of X? It's written in the formula sheet as well. It looks like this: sigma X squared P minus expected value of X whole squared. That's the formula for variance. What is sigma X squared P? 225/56. Subtract from this square of 15/8. And that will be your variance. You can see what that is. Okay, this is giving me 225/448. You can write this in decimals as well. In decimal, it turns out to be 0.5022. It says 0.5022, 3 significant figures, and that's your final answer. That's what we wanted. All right, that's part C. Let's move on. And that was one question that you asked about from this paper. Okay, from 5-2, the next one is question number 5. Okay. So this is simple normal and then inverse normal in the second part. And then this expected value. Okay. Question number 4 is a probability question, conditional probability. Last part. No, intersection. Okay. And then conditional. All right. So this is the next question that you guys are asking about. Question number 5 from this paper. Okay. Is it about the last part? Okay, so those of you who have asked this question, are you asking about the last part of this? Because the first part and the second part, I think they look pretty straightforward. But what I'll do is I'll actually do this for you as well, because a lot of people make mistakes here. Let me actually go through this whole process with you. How to draw a stem and leaf diagram. It's a very easy part, but it's very easy to lose marks in this as well, because they deduct marks for very simple things, very small things. Okay. So let's actually do this. How do you draw the stem and leaf diagram? And then also there's a specific way to find interquartile range. I'll also explain that while I do this. Okay, stem and leaf diagram. It's a back-to-back stem and leaf diagram. That means you would have stem in the middle. Always do it with a pencil so that you can erase something if you need to. It's also a diagram, right? You can do this with a pencil. Okay, so this is the stem that's going to be in the middle like this. Now, on the left side and the right side, do they specify what should be on the left and right? They don't. Sometimes they specify that, and it's necessary to do it exactly as they ask you to do. Okay. Now, in this case, they haven't specified, so we can have any of them on the left and right. We can say we have this result on the left side, and then the other one on the right side. Now, remember, leaf can only have a single digit. Okay, leaf can only have a single digit. Now, most of these numbers are two-digit numbers, right? So what are we going to have in the leaf? The leaf is going to start from 0. Why? Because we've got one-digit number as well. And then what's the maximum number that we have? In both of these data sets, 42. Do we see a larger number than that? No. So the minimum value of the data is 0, and the maximum value of the data is 42. This is the data that we need to represent. What we can do is we can have a stem like this. We need to start from 0. Why? Because there are one-digit numbers as well. That means the tens digit for that is going to be 0. And then we cannot miss any number up to 4. Sometimes what happens is you don't have any values corresponding to some stem. For example, if there was no 22 and no 28 here, and yeah, if these two values did not exist, that would not mean that you skip 2 from here. You can't skip any value. In STEM, values have to be in order, and you cannot skip any number. Okay, you have to write down all values. Okay, so 0 to 4, we write values like this way. Now, these lines are necessary. You have to draw vertical lines. If you don't draw vertical lines, you lose a mark. Okay, if you just leave some gap like this, assuming that it's understood that you have stem in the middle and then leaves on the right side, you lose a mark. Drawing this vertical line is necessary. Okay. Now, let's write down these values. First of all, single digit numbers, since they have to be sorted, you have to first identify them. 6, 8, and that's it. For the first set of data, we have 6 and 8 here. Now, the values have to be sorted. Values close to stem, they should be smaller. Values away from stem, they should be larger. So we have 6 here, and we have 8 here with some gaps. Okay. All right. Now, the next value, so these are done. You can cancel them out so you know that you've already used them. Okay, now ones. We have 12, 15, 10. First, highlight those values. So you can write them in order. Now, the smallest value is 10. And then there are 2 10s. So we say 0, 0. These values should be aligned. 0, first 0 under 6, the second 0 under 8. And now the gaps between values, they have to remain consistent. Whatever is the gap between these values, it should remain consistent for the next values after this. Okay. Again, that's why it's important to do it with a pencil, because sometimes when you're drawing it, you end up running out of space, you have to erase that and then redraw that so you have enough space on both sides for the gaps to remain equal. Okay, so we have 2 10s and then we have 12, 15, and 16. So that means you have 2, 5, and 6 here. And then similarly for the rest of the data. Now let me do the rest of it quickly. So you have 12, 15, 10, 10, 16 done. So I 12, 15, 10, 10, 16. Yeah, so we're done with them. Now in 20s, we have 22 and 28. So we have 2 here and 8 here. Again, they should be aligned. Then in 30s, we've got 36. So that's 6 here. And then in 40s, we have 42, we've got 2 here. Let's just count those values. We had 11 weeks there. So this should be 11 values, 1, 2, 3, 4, 7, 8, 9, 10, 11. That's done for the first one. Now for the second one, what's the smallest value? 0. So we've got 0 here. And then we have 2. Again, the gaps have to remain constant. And then we have 10. So we had 9 there as well. I missed that. Okay. Then we have 10, 11, 12, 15, 16. These 5 values. 10, 11, 12, 15, 16. And then in 20s, we don't have any value here. In 30s, we have 2 and 6. Again, all of them should be aligned. And finally, in 40s, we've got 0. And you can count them. These are 11 values. This is what your stem and leaf diagram is going to look like. And you also have to write down the key. There's 1 mark for writing down the key. What's the key going to look like? You'll draw 2 vertical lines, write a number in the middle. Any number, let's say 3, and then maybe 4 on the left side, and then maybe 5 on the right side. Now, what this does not have to be there in your stem and leaf diagram. Okay, you can write any numbers, and all of these numbers should be different. Do not use same numbers anywhere here. Stem should be different. The number on the left side should be different. The number on the right side should be different. Otherwise, the key will not be clear. You would say this means 34, is there a unit here? Centimeters. 34 centimeters. This is important. If you miss this unit, you lose the mark. You have to write down the unit here. 34 centimeters for this first result, and 35 centimeters for the other result. You have to mention this key here. All right, so these small things are very important. If you write commas here, you lose a mark. You can't have commas. You have to have just spaces, no commas, no full stops. Okay. It has to look exactly like this, otherwise you lose marks. All right. No, for pencil, it's you don't lose marks. In fact, they explicitly mention in the start of the paper, that diagrams can be drawn with a pencil. Okay, this is a diagram. You can do this with a pencil. Okay, so that's what the stem and leaf diagram looks like. Now it says find the median and interquartile range. The data is ungrouped. For ungrouped data, we know that the median formula looks like this: n plus 1/2. What's the total number of values? 11. 11 plus 1/2. That means 6 value is going to be the median. Now, stem and leaf diagram sorts your data as well, right? So these values are sorted. What are we looking for? Okay, for this result, what's the median? 1, 2, 3, 4, 5, 6. This is going to be the median. Okay, now it's not 5. Median is not 5. It's 15. This is the stem. 15 is the median. We say this is 15 centimeters. That's the median. And then you have to find interquartile range. How do you find interquartile range? You have to use exactly this method. Do not use formulas. Otherwise, you'll sometimes get wrong answers. Okay. What do? This is the median. Your median divides your data into 2 parts. One part that is on one side of the median, values less than the median. And then one part, values on the other side of the median, values that are greater than the median, these values. You find the median for each of these parts. What's the median for these 5 values? Median for these 5 values is this number here. This is going to be your lower quartile. What's this number? 10. Lower quartile is 10 centimeters. What about the upper quartile? You'll find the median for the values on the other side, the green values. The middle number there is this number. What's that? That's 28. So the upper quartile here has to be 28. The lower quartile is 10. The upper quartile is 28. And now you can find the interquartile range. What's the interquartile range going to be? 28 minus 10, that is equal to 18. Now, some of you will tell me that you're getting the same result using some formula. Yes, you might get the same result in this question, but not for all questions. That will not always work. Okay. So that's the interquartile range. Part C. Now it says the median lower quartile and upper quartile of the weekly snowfall for 𝗪𝗲𝗏 are 12, 9, and 32 centimeters respectively. So we've got the median lower quartile and upper quartile given for this. Use this information and your answers to part B to compare the central tendency and the spread of the weekly snowfall in these two results. Central tendency. What is central tendency? Central tendency is mean, median, mode. Which measure are we using here? Median. So you have to compare the median. Okay. Now don't just write that median is high for this, median is lower for this. You have to contextualize that. So median represents average, right? For, let me actually write that here. For these two results, let's call them D and L. We know the medians, we know the lower quartiles and the upper quartiles. And using that, we can find the interquartile range as well. So we know the median. Median for the first result was 15. For the second one, it is 12. And the interquartile range for the first one was 18. For this one is 32 minus 9. What's that? That is 23. This is 23. You have to compare their central tendency and spread. Median is a central tendency measure. What's the data representing? Data is representing weekly snowfall. Now, you have to contextualize this. Use the data that is given. Don't just write that median is higher for this, standard deviation, interquartile is higher for this, lower for this. But what is it? How does it relate to the data that is given? The data is about weekly snowfall for 11 weeks. Okay, at both of these results. You would say median represents an average number. So on average, central tendency measures, mean, median, mode, they represent an average. You would say on average, weekly snowfall is more at this result than the other result. And then similarly, you make a comment on the dispersion on spread using the interquartile range. You would say the weekly snowfall in this first result is less varied, or you can say has less variation as compared to the other one. Right? Because this number is higher, that means its spread is more. This is what you could write here. These are two statements that you have to write. You can write them in your own words, but you have to contextualize them. Relate them to the data that is given. Okay, don't just write general statements. Median is higher and interquartile range is higher or lower here. Explain what that means. Okay, interquartile range is telling you how much variation is there. Median is telling you the average of that rainfall. Okay, that's snowfall in fact. And you also have to make sure that you use the word snowfall in your statement. Otherwise, again, they can lose mark. You can lose marks for that. Okay, because you have to make sure that you use the context that is given there. Let's move on to the next one now. Question number 5, we're done with. Now, the next one that you're asking about from this paper is question number 6. Let's have a look at this now. Mr. and Mrs. Emmett with their 2 children and Mr. and Mrs. Baker with their 3 children are visiting an activity center together. They will divide into groups for some of the activities. In how many ways can the 9 people be divided into a group of 6 and a group of 3? Now, we have 9 people in total. We want to make a group of 6 and a group of 3. So we can say out of 9, select 6 people for one group. And then the other 3 would automatically go to the other group, right? Or if you want, you can also do it like this. You can say 9C6 multiplied by 3C3, that the remaining 3 people, they go to the other group. Okay, and that will give you the result. You can also do the other way around. You can say select 3 people out of 9 for one group, and then 6 out of 6 for the other group. Both of them should give you the same result. Okay, you can use any of them. Let's see what this is. 9C6 multiplied by 3C3, that's going to be 1. That's 84. Okay, that's the first part, fairly straightforward. Let's move on to the next one. Now it says 5 of the 9 people are selected at random for a particular activity. Find the probability that this group of 5 people contains all 3 of the Baker children. We're looking for probability. We're talking about people, they're all different. Remember, people are never identical. Even if they're twins, they're different. Even if they're identical twins, they are different people. Okay, don't consider them identical. Find the probability that this group of 5 people contains all 3 of the Baker children. Okay, so we are selecting 5 out of the 9 people. We want probability. What's the total number of possible selections? Where we don't have any restrictions. We have 9 people. We want to select 5 out of them. That's just 9C5. That is going to be the denominator in that probability that you calculate. Now, what about the favorable outcomes? The condition is that you need to have all 3 of the Baker children. Now, let's look at the group that we have. We have Mr. and Mrs. Emmett and their 2 children. Mr. and Mrs. Baker with their 3 children. So we have 4 people here and then 5 people there. Okay. Now, all of these 3 children have to be selected, right? That's what they're saying. Find the probability of all Baker children being there. Now, there are 5 people that we need to select. If the Baker children have to be there, that means B1, B2, B3, they're already selected. We have only 2 places left for the rest of the people. How many people are we left with? We have 6 people left. Out of those 6 remaining people, we need to select 2. Okay? So these are the possible outcomes where you have the Baker children selected. You can just find these 2 numbers, 9C5 and 6C2, and you just divide them. Let's do that directly. Probability is going to be 6C2 divided by 9C5. Right? The number of favorable outcomes, that's going to come from 6C2 divided by the total number of possible outcomes. You can see what that turns out to be. 6C2 is 15 over 9C5. That is 126. Can we simplify this? 5 over 42. That's the result that we get from this. Okay. 5 over 42. That's the probability that we were looking for. Make sense? That's the second part here. Let's move on. Now it says all 9 people. It says all 3 Baker children are selected. So we could say if we wanted, select 3 out of those 3 Baker children. It doesn't make any difference, right? All of them have to be there, right? 3C3. That's just 1. 3C3 is 1. So if we wanted, we could do that as well. We'd still get the same thing. Okay? What if it had said 2 Baker children? Then what you have to do is, you have 2 Baker children. You would do 3C2 for that. Select 2 Baker children. And then you have 3 remaining places. That's 6C3. That will be 3C2 into 6C3. Okay, in that case, you have to consider the Baker children separately because you have to choose which 2 of the Baker children we want, because again, they're all different. They're not letters that we can just select directly without considering that which of the letters are going to be there. They're all different people. Okay, so that's the probability. Let's move on now. It says all 9 people stand in a line. Find the number of different arrangements in which Mr. Ahmed is not standing next to Mr. Baker. Now, all 9 people are standing in a line. Mr. Ahmed is not standing next to Mr. Baker. 2 people that you want to separate, we can use both methods. Dashes and stars method, total minus together method, both methods would work. Okay, you can use any of them. What are the total number of possible arrangements? Subtract from that Mr. Ahmed and Mr. Baker together. Okay, what are the total number of possible arrangements? 9 factorial. Remember, there are no repetitions. That we're talking about people. Minus A and B together. If we put them in one single box, we've done this so many times now. How many boxes do we have? 8 boxes. We can arrange them in 8 factorial ways. However, then A and B can also switch places with each other, right? In how many ways can they do that? 2 factorial. That's what we get, right? So you can make those that boxes representation. You would have 9 boxes initially. Merge 2 of them, you get 8 boxes. In one big box, you are putting A and B together. So that's 8 factorial into 2 factorial for A and B switching places. And that should give you the result. You can see what that is. 9 factorial minus 8 factorial into 2 factorial. Okay, so that is 282,240. That's the result that we get from this. Let's move on. Part D. Now it says find the number of different arrangements in which there is exactly 1 person between Mr. Ahmed and Mr. Baker. Now, this is the type of person that is coming again and again in recent papers. Let's look at this. So we had 9 boxes initially, right? For 9 people, let's say we have these 9 boxes. Okay. Now what we want is, we want exactly 1 person between Mr. Ahmed and Mr. Baker. What we can do is, we can say, let's say if Mr. Ahmed was here and Mr. Baker was here, and there's 1 other person between them. Now this box has to move together. Okay. Now, in how many ways can we, first of all, fill the rest of the boxes? How many boxes do we have left? 1 here, and then 2, 3, 4, 5, 6, 7. There's 7 places left, and we have 7 remaining people. In how many ways can we arrange those 7 people? 7 factorial ways. Okay, so the remaining people can be arranged in 7 factorial ways in these boxes. All right. Now, this box could also move around. Right now, we've got 6 small boxes on the right side. It could also be that we have 1 box on the left and then 5 on the right side, like this. And then similarly, there are many other possibilities as well. So what can happen is, this big box can remain here. That's one possibility. Or it can go, sorry about that. Okay, so this one big box can either remain in this position, or it can go here, here, and in all of these possible positions. In how many ways can this box move now? Initial position, that's one case, and then 2, 3, 4, 5, 6, 7. It can move around in 7 ways like this. Okay? So we multiply this by 7. And then A and B, they can also switch places with each other. Right now, we have considered that A is on the left side and B is on the right side. They could also switch places. And how many ways can that be done? 2 factorial ways. And that should give you the result. 7 factorial into 7 into 2 factorial, you can see what that is. That is 70560. And that's your final answer. 70560. That is what we were looking for in the last part. Okay, this is the type of question that is coming again and again in recent papers. You need to make sure that you understand this very well, because it's coming very frequently now in the last few years. Okay, no problems with this? Can we move on now to the last paper that we want to do today? All right, good. Let's move on to the last paper now. November 2020, paper 5, variant 3. Okay, some of you were not here in the beginning. Just a reminder, we might have a class tomorrow as well for any last minute help that you need. You should let me know what you would prefer doing in our tomorrow's class, okay? One possibility is that we do difficult questions from June 2020 papers. That's one session that we're left with. Or we could make it kind of open-ended. You can come with any questions that you have from any year, from anywhere, any difficult questions, and we could discuss them. All right, so it's going to be one of those two things. Let me know which one you would prefer. I'll also post that in the group so that I can get an idea of what most people would prefer. So we either just focus on June 2020 papers, or we make it open-ended. So you can ask any questions that you have. Yes, Ibrahim, I'll upload the recording right away after the class ends, okay? All right, so this is the last paper that we want to do today. Difficult questions from this paper. Let's try this now. Please let me know about this paper as well, the questions that you find difficult, so we can decide which ones we want to do. So there are not many votes in this one yet. P53. Please take a minute, respond to the poll. Let me know the questions that you find difficult from this paper. All right, let's start with this then. So there are 3 questions that I see you guys have voted for, questions 2, 3, and 6. This is November 2020, paper 5, variant 3. Okay, so we are going to be doing difficult questions from this paper as well. Let's begin with this. So the first question is about normal distribution. This is simple normal in the first one. Then we have this inverse normal. Question number 2. Okay, let's start with this one. Question number 2 from this paper. An ordinary fair die is thrown until a 6 is obtained. Does that remind you of something? You're repeating something until you get your first success. That is geometric distribution. Okay. Now, what are you calling a success here? Obtaining a 6, right? Find the probability that obtaining a 6 takes more than 8 throws. This is what we're calling success. So the probability of success, therefore, is it's an ordinary fair die. That means 6 sides, equal probabilities for all sides. P is going to be 1/6, right? Probability of success, obtaining a 6, the probability that is 1/6. Probability of failure, that will be 5/6. It's a geometric distribution because we're looking for our first success. Find the probability that your first success takes more than 8 throws. More than 8 throws. Probability of x being greater than 8, that is what we want to find out. Remember, for geometric distribution, we also have a direct formula for inequalities. And what does that look like? X greater than r, that equals q raised to power r. This is something that you definitely have to memorize. And then you can convert everything else to this form. Okay? Or you can also, if you find it difficult to convert everything to this form, you can memorize another one as well. Basically, the complement of this, that will look like this: x less than or equal to r. That will be 1 minus q raised to power r. So either convert everything to this form or this form, and then you can use them. Okay. So in this case, it's already in that required form, probability of x greater than 8. That gives you q raised to power 8. Q is 5 over 6, so that's 5 over 6 raised to power 8. You can see what that turns out to be. That will be the probability. Okay, what's this number? (0.23256). If you want to round it off, make sure that you round it up to 233. If you write 232 here, you lose a mark. Okay. Or you can write 4 significant figures and that will be fine. But if you do round it off to 3 significant figures and end up not writing the last digit as 3, that will make you lose a mark. Okay. All right, now it says 2 ordinary fair die are thrown together until a pair of 6s is obtained. So now we're throwing 2 fair dice. How many outcomes is that? 6 outcomes from the first one, 6 from the second one. The total number of outcomes is 6 times 6, that is 36. Pair of 6s, what does that mean? The first is a 6, the second is a 6. What's the probability of success? This is what we're calling success now. Getting a pair of 6s, this is success. What's the probability of success? The total number of possible outcomes, that is 36, right? 6 times 6, 36 outcomes. Probability of success, 6 6s, 1 out of those 36 outcomes. So success probability would be 1 out of 36. And then what about probability of failure? That will be 35 out of 36. We want to find the probability. In fact, we want to find the expected value of x. It's a geometric distribution, right? What's the formula for expected value of x in a geometric distribution? That's 1 over p. So that's 1 over 36, and that gives you 36 as the result. That's the expected value. Okay, for binomial, it's NP. For geometric, it's 1 over p. Now, find the probability that obtaining a pair of 6s takes either 10 or 11 throws. Pair of 6s, again, we're talking about pair of 6s. This is what we're calling success. Getting a pair of 6s takes either 10 or 11. Now, it does not explicitly mention that here, but the question statement basically implies that they're talking about obtaining your first pair of 6s, right? It takes 10 throws to obtain a pair of 6s. That means the first 9 throws, they're all failures. You haven't gotten a pair of 6s in the first 9 throws. Okay, so this is still geometric distribution. We're talking about our first success. Okay, and the success is defined as pair of 6s. What's the probability of that? 1 over 36. Probability of failure? That's 35 over 36. Now, what we want to do is we want to find the probability of x being either equal to 10 or equal to 11. So we want to find these two probabilities and then add them up together. There's an or between them. It could be the first case or the second case. Any of them will work. There's an or between them. So we find each probability and then just add them up together. Let's see what we get from this. Remember the binomial the geometric distribution formula. That is q raised to power r minus 1 times p. So this becomes 35 over 36 raised to power 10 minus 1, which is 9, into 1 over 36, plus 35/36 raised to the power 10, which is 11 minus 1 basically, into 1/36. And that will give you this probability. You can see what this turns out to be. Okay, what's this number? Does anyone have the result from this? Okay, 0.042523 significant figures. Okay, that's the probability that you have here. Part C, and that's it. That was not that complicated, right? Okay, that was question number 2 from this. Let's move on to the next one that you've asked about from this paper. Question number 3. Okay. All right, let's have a look at this. A committee of 6 people is to be chosen from 9 women and 5 men. Find the number of ways in which the 6 people can be chosen if there must be more women than men on the committee. Now, what we do is we write the number of men. There are 5 men. We write the number of women. There are 9 women. What they want is they want the number of women to be more than the number of men. And the total number has to be 6. What are the possibilities? You're going to have 2 men and 4 women. You could have 1 man and 5 women, or you could have 0 men and 6 women. Right? These are the only 3 possibilities that you have. Find each of these cases, add them up together, and that will give you the result. All right. So what about the first one? Out of 5 men, we have to select 2. That's 5C2. And out of 9 women, we have to select 4. Right? And then in the second case, out of 5 men, we have to select 1. And then out of 9 women, we have to select 5. And then finally, 5C0 into 9C6. Find each of these cases, add them up together, and that will give you the result for this. Okay. 5C2 is 10 into 9C4. That's 1260, the first one. 5 into 9C5, that is 630. And then 1 into 9C6, that is 84. Add these cases and see what that gives you. This is 8946. This is what we get from this. Is that calculation correct? Okay, no, I am also multiplied by answer here. That's 1974, I'm sorry. This is 1974. Okay, that's the result that we get from this. Fairly straightforward, first part. Now it says, the 9 women and 5 men include a sister and a brother. A sister and brother, okay? Find the number of ways in which the committee can be chosen if the sister and brother cannot both be on the committee. We don't want both of them on the committee. Now, what does that mean? So we have a sister and brother. We can either have the sister and not the brother, or we can have the brother but not the sister, or we can have none of them. These are the 3 possible cases. This case we do not want. Okay. Now, we can either find these 3 cases, or it's easier to find the total cases and subtract from that this case, where you have both the brother and sister selected. Okay, from the total, we can eliminate this case. That will be quicker. Or you can find these 3 cases directly as well. Both methods would work. All right. Now, if we do total minus this last case, let's see how that would work. Total minus both S and B selected. Okay. Now, is there a condition for this? 6 people are to be chosen from 9 women and men. There is no condition here. Okay, so there's no condition on the number of women and men anymore. So what's the total number of arrangements? A total number of combinations? Out of 14 people, we have to select 6, right? Yeah. 14 say 6. That's the total number of possible combinations where we don't have any restrictions. Now subtract from that the case when the sister and brother are both selected. Now, if they're both selected, you see, you've got 6 places on the committee. Brother and sister are already selected. How many people are we left with? 12 people. Out of those 12 people, we need to select how many more? 4 more. So that's 12C4. Okay, and that will give you the result. Okay. Makes sense? You can see what the strengths are to be now. (14C6 minus 12C4), and that's giving me 2508. And that's our final answer here. 2508. Make sense? That's part B. Let's move on. That's it. That was the permutation combination question. Again, not that complicated. This is binomial and then binomial to normal approximation. No one has asked about question number 5. Okay. First is V and the last is E. Probability that both R's are together, given that all 3 E's are together. What about the second part? I think this looks kind of tricky. Let's actually do this question as well from this. The first part is fairly straightforward. You have 8 letters in the word reserved. They are arranged in a random order. Okay, 8 letters in this word are arranged in a random order. Find the probability that the arrangement has V as the first letter. So V has to be the first letter, E has to be the last letter. We have 8 letters in total. How many letters are we left with in the middle? 6 letters are left in the middle, right? These are 6 letters in the middle. Let's make 6 boxes for them. What are those 6 remaining letters? R, S, E, R, E, D. 1 E is there, V is there. Yes, these are the remaining letters, right? Now, in how many ways can you arrange these letters? There are 6 letters, 6 factorial, and then 2 R's, that's 2 factorial, 2 E's, that's 2 factorial, and that should give you the result. 6 factorial over 2 factorial and 2 factorial. All right? No, it should be 14C6 there. That's 14 people in total. That's 14C6. Okay, so you can see what this turns out to be. 6 factorial divided by 4, and that's giving me 180. And that's the result that we get from this first part. Okay. Okay, sorry. We were looking for probability. Yeah, you're looking for probability, right? So this is when you have V as the first letter and E as the last letter. These are your favorable outcomes. Now find the total number of possible outcomes if there were no conditions. Total possible arrangements, what would they be? If you consider all letters, we have 8 letters in total. That's 8 factorial divided by 2 factorial because of the 2 R's, and then 3 factorial because of the 3 E's. You can see what this turns out to be as well. 8 factorial divided by 2 and 6. That's 3360. And that should give you the probability. Divide these two numbers and see what that is. 180 divided by 3360. That will be the probability. That's 3 over 56, and that's what we were looking for in the first part. Okay, pretty straightforward. Just make sure that you find probability and not just the number of possible arrangements. We have to find probability. We have to find probability here. Okay, that's the result that we get. Okay, now let's move on. Now it says find the probability that the arrangement has both R's together, given that all three E's are together. Now, this is conditional probability. What is given has to be the denominator. When you're finding probability, what's given has to be the denominator. Let's find this case first of all, where three E's are all together. How do you find this case? Let's make this box as representation where the three E's are all together. That's the first case that I'm finding. Three E's together, because that's the that's the case that is given. That has to be the denominator of the probability formula. Okay, three E's together. We have 8 letters in total, so we can say we have 8 boxes. Since we want the three E's together, we can merge 3 boxes, put the three E's inside that single box. What are the remaining letters? The word was reserved, so the remaining letters are R, S, R, V, D. These are the remaining letters. In how many ways can we arrange them? There are 6 boxes now, that's 6 factorial. But then you have 2 boxes that are identical, R and R. We have to divide by 2 factorial because of that, and that will give you the result for this. E's are all identical, so we don't have to arrange them. 6 factorial divided by 2 factorial, that's 360. These are the number of outcomes where the three E's are together. That is what is given. This will be the denominator in that probability. Okay, remember the formula? Probability of A given B, that is equal to probability of A intersection B. That means where both of those things are together, are true, divided by probability of B. We have found this for now. Probability of what is given. Now, what is the probability that we want to find out? Both R's are together. So now we want to find the probability of this intersection. That all E's are together and both R's are also together. The intersection, where both those conditions are true. Let's find that out. 3 E's together. That is still going to be the case, right? We're looking for intersection. And 2 R's together, both R's together, basically. In how many ways can we arrange this now? Again, we could consider this box's representation. We could say we had 8 boxes initially. We merged 3 of them and put 2 E's in them. And then what we can also do is we can merge 2 other boxes to put the 2 R's in them. And then we have 3 boxes left outside. And they would have the letters S, V, and D. In how many ways can we arrange this now? There are 5 boxes. We can arrange them in 5 factorial ways. They're all different, and that's it. We don't have to arrange E's and R's because they're all identical. We don't have to consider their arrangements. This is just 5 factorial, and that is 120. What's the probability then? Probability of intersection, that is 120, divided by the probability of what is given. That's 360. Not the probability. In fact, in the numerator, we have the possible outcomes when both conditions are true. In the denominator, we have the outcomes where 3 E's are together, the case that was given. Okay, you can see what this is. 120 over 360, what does that give us? 1 over 3. That's going to be our final result. So the probability is 1 over 3. Is that okay? Why do we not do 3 factorial for E's? Well, because they're all identical. Even if you were to do that, even if you were to do 3 factorial for the 3 e's, they're all identical. We would have to divide by 3 factorial as well. So that's 3 factorial divided by 3 factorial. That's just going to be 1. So it's equivalent to not considering that at all, right? Because the arrangements for e's do not matter. They're all identical. If we were to consider that, that will be 3 factorial over 3 factorial. So it gets cancelled out anyway. All right, that's your part B for this. Let's move on. Okay, so the next question that you guys have asked about is question number 6. Is that the last one from this paper? No. We have question number 7 after that. That's histogram. Okay, estimate for the mean number of incorrectness. Okay, all right. So 7 is easier after that. Let's just do question number 6, and then we end with this. If you don't have any other questions. Okay, so the last question from this paper, 3 coins A, B, and C are each thrown once. Coins A and B are each biased so that the probability of obtaining a head is 2 over 3. Coin C is biased so that the probability of obtaining a head is 4 over 5. Okay, so this probability is 2 over 3 for A and B. For C, probability of a head is 4 over 5. Show that the probability of obtaining exactly 2 heads and 1 tail is 4 over 9. Now you can make a tree diagram for this to simplify things, okay? Or you can just think of it in your head, whichever way you prefer, it could work. Let's think of it using a tree diagram because it's not going to be that big, and that will help us, I think, with the next part as well. Yeah. So if we make a tree diagram once, that will make things simpler. Let's do that. So let's first of all consider the first coin. Let's say that's A, and you have B, and then C. They're all thrown together, so it doesn't matter which one comes first or later, right? So we have A. It could either give you heads or tails. And then B could either be heads or tails. Heads or tails. And then here, again, you could have heads, tails. Heads, tails. Heads, tails, and heads, tails. Right? These are the cases that you've got. There are 8 possible outcomes in total. You can see them here, 8 possible outcomes. Now, for A and B, probabilities are 2 over 3 for head and 1 over 3 for tails. 2 over 3, 1 over 3, 2 over 3, 1 over 3. For C, it's 4 over 5 and 1 over 5. And it's the same for all of these branches, okay? Let me just write that. So once you've done this effort, now you can just use this tree diagram to do the whole question. Okay, show that the probability of obtaining exactly 2 heads is 1 tail, and 1 tail is 4 over 9. 2 heads and 1 tail. How can you get 2 heads and 1 tail? You can have head, head, tail, head, tail, head, and tail, head, head. On this tree diagram, that's these parts. Head, head, tail, head, tail, head, tail, head, head. Just add all of those cases and that will give you the result. Okay? What's this one? 2 over 3 into 2 over 3 into 1 over 5. What does that give us? 2 into 2 divided by 3 and 3 and 5. That's giving me 4 over 45. And then the second case, that is 2 over 3 into 1 over 3 into 4 over 5. Now, remember, we can't find one of these cases and multiply that by 3 because these probabilities are all different. Okay, so can't do that thing where, that we did in one of our earlier questions, that we find one probability and then multiply by 3 factorial over 3 factorial over 2 factorial. That does not work here. The reason for that is, you can see this probability and this probability, they're different, right? So we can't just add the same probability 3 times. We have to calculate each one of them separately. Okay, what does this turn out to be? 8 divided by 45. So this is 8 over 45. And then the last one, this case is 1/3 into 2/3 into 4/5. This is also 8/45. Add these cases up and you get your result. Okay. So when you add them up, you get 20/45, which is 4/9. That's what you had to do in the first part. Now it says the random variable x is the number of heads obtained when the 3 coins are thrown. Draw up the probability distribution table for x. So now we want x values and then their corresponding probabilities. Let's see what this turns out to be. X, probability of x, number of heads obtained. What could be the number of heads obtained? You could have 0 heads, 1 head, 2, or 3. These are 4 possible cases. We have already found the probability of obtaining 2 heads. That was 4/9. So we know that this probability is 4/9. Now, it's actually going to be much quicker, very quick, if you just find the probability of obtaining 0 head, because that's just one case. Tail, 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 right? So probability of x equals 0, that means it's just tail, 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 right? What's this probability going to be? 1/3, and then 1/3 and 1/5. And that will give you a probability for x equals 0. That's 1/45. So this is 1/45. And then the last one is going to be very simple as well, because that's all heads. If you're getting 3 heads, that means x equals 3. You have all heads. In that case as well, you don't have to consider different paths because there's only one path on the tree diagram that gives you heads and heads. What do you get from that? 2/3 into 2/3 into 4/3. Sorry, 4/5. 2/3, 2/3, and 4/5. All right. And you can see what that is. 16/45. This is 16/45. And now, since these are fairly straightforward calculations, you're pretty sure about these numbers. You can find the remaining by subtracting these numbers for 1, right? So 1 minus 1/45, or just subtract this 45 and start 45 minus 1 minus 4 minus 16. And that's going to be 24. This is going to be 24/45, right? Subtract the rest of the probabilities from 1 and you will get this. And that's your final result. That's the probability distribution table. Once you have this, you're given that expected value of this, find the variance of x. That's fairly straightforward after this, right? You have to find variance of x. You can find, back to this and just move it down a little. Denominator of 2 was different. That doesn't matter since they told you it's 4/9 in the first part. You could just use that. But if you want, you could also write it as 4 into 5. That's 16/45. You could also write this as 16/45. That's also all right. Is that what you get? No, 4/9 is 20/45. Sorry. Okay. I understand what you mean by that. So that means the other probability that I calculated, that was wrong. I'm sorry about that. You're right. So this was 4/9. So I did not do the subtraction properly then. Okay, let me do that. 1 minus 1/45 minus 4/9 minus 16/45. That's 8/45. So this should have been 8/45. Yes. Yeah, I considered 4/45. That was wrong. I'm sorry about that. Yeah, so this is 8/45. That's correct. All right. So now that we have this, we just have to find variance of x. Let's find x square p. 0, 8/45, 4 into 4, that's 16/9, 9 into 16 divided by 45, that's 16/5. That will give you sigma x square p. What's that? 8/45, 16/9, 16/5. That's 232/45. 232/45. So what's the variance of x then? Variance of x is given by sigma x square p minus expected value of x whole squared. You found sigma x square p there, that was 232/45 minus the expected value, which is 32/15, square of that, and that should give you the result. That's giving me 136/225 in decimals, that is 0.60444. So that's 604. That is the variance that we were looking for. Okay, and that's our final result. That's question number 6, part C. Okay, and that's it. That was the last difficult question that you wanted me to do from this paper. And we will end this here. The next is just about histogram. You have to make sure that you adjust these gaps before you draw that histogram. Okay, make sure to adjust these gaps, and then your class width will be calculated using those adjusted intervals. This will be 5.5, 10.5, 20.5, 40.5, 70.5, 0.5. So class widths are going to be calculated from these. So for the first one, the class width is 5, and then 5, 10, 20, 30. All right, and then you calculate frequency density by doing frequency over class width, and then draw that histogram. Okay. Greatest possible value of interquartile range? Well, you would get an interval for lower quartile. I'm going to show this to you as well. Lower quartile will be, where is the lower quartile will be? 91/4. So I'll just tell you about this quickly. 22.75. Lower quartile is going to be an 11 to 20 interval. So lower quartile, we're talking about number of incorrect notes. Okay, so this is a discrete variable. Remember, it's a discrete variable. Whereas the lower quartile going to be 11 to 20. Okay, so you can figure that out. I expect you to be able to do that. And then 91 into 3/4, that's 68.25. That will be in 21 to 40 interval. Okay, so for this part, you will find the upper quartile and the lower quartile. Upper quartile is in this interval from 21 to 40. Now what they're asking you for is, find the greatest possible value of interquartile range. How do you do that? Greatest possible interquartile range. Interquartile range is upper quartile minus lower quartile. Okay. Interquartile range is upper quartile minus the lower quartile. Now, for finding the greatest possible interquartile range, you have to use the maximum value for upper quartile and the least value for the lowest lower quartile. That is when this difference is going to be maximum. Now, what's the maximum possible value of the upper quartile in this data? 40 minus 40 minus the least possible value for lower quartile. What's that? That's 11, and that will give you 29. Now, here is an important thing to understand. We were talking about number of incorrect notes here. Number of incorrect notes, that is supposed to be a discrete variable. That is an integer. Okay. So in this case, we just do 40 minus 11 like this. If it was a variable that was continuous, if it was a continuous variable, okay, that means if it was, for example, time or length or height, something like that, the greatest possible interquartile range that you find here, it would have been found using the adjusted intervals, because those values could be in decimals as well. If you had a continuous variable, length of something, time, right? Things like that. Then you would consider this interval, 10.5 to 20.5, and then this would be 20.5 to 40.5. In that case, the greatest possible interquartile range would be 40.5 minus 10.5, and that will turn out to be 30. In this case, the variable is discrete. That means in this case, it can only take integer values. So here you just do 40 minus 11. If it was a continuous variable, you would have done 40.5 minus 10.5, because those values could be in decimals as well. Okay, I hope that makes sense. You can do the rest of the parts. That's it for today. So we're done with, we have done difficult questions from 3 papers today, 5.1, 5.2, and 5.3 from November 2020. All right. Okay, let me repeat that again. I just said, in this case, the variable that we're talking about, that was number of incorrect nodes. Number of something. That's supposed to be an integer. And the intervals are from 11 to 20, 21 to 40. You just use 40 minus 11 here. However, the adjusted intervals that we found here, they were actually 10.5 to 20.5, 20.5 to 40.5. 10.5 to 20.5, 20.5 to 40.5. If it was some other variable, for example, length, height, time, right? Something like this, that can also have decimal values, right? Time can be in decimals, height can be in decimals, length can be in decimals, or any other variable that can take decimal values as well. You would have used 10.5 as the lowest possible value for interquartile range, because this is the actual boundary of that interval there. Because if some length was 10.8, for instance, or 10.6, for instance, it would be rounded off to 11. So this is also part of this interval, 10.5, values more than 10.5. And from the second interval, you would have taken 40.5. Again, because the values can be in decimals as well. And the interquartile range, the greatest possible interquartile range, in that case, if it was a continuous variable, it would have turned out to be 40.5 minus 10.5, and that's 30, and not 29. It's not given that you would not be given that this variable is continuous or it's discrete. Generally, you have to understand the difference between the two types of variables. Continuous variable is something that can take any decimal value. Discrete variables are those that can only take some specific values. Generally, in your syllabus, you only get integers. Okay. You don't have to memorize that time and height are continuous. You just have to use some common sense to know that time can also be decimals, right? In decimals, right? 2.3 hours, 2.7 hours, 2.5 hours. Height can also be in decimals, right? Yeah. You have to think of it logically, right? Okay. In the cases of yes, so in continuous variable case, you would find those intervals using the adjusted intervals. So the adjustment that you did here, if it was a continuous variable, you would use these numbers instead. Okay. All right, so that's it for today then. Tomorrow, hopefully, we'll have another session as well, in which we will either do June 2020 session, or it could be just open-ended, where you can tell me which specific questions you want me to discuss, and we could just discuss those questions then from any paper from any year. So I'll ask in the WhatsApp group what most of you prefer. Do we just focus on June 2020 papers because that's one session that we're left in the last 5 years? Or we could make it open-ended. But I'll post that in the group and you can respond to that. All right, so that's it for today. I'll see you again tomorrow. You're welcome. Allah Hafiz.